Okay, so the I've talked a fair bit about linked lists. These videos, let's look at that real quick. So, yeah, quite a bit of talk about linked lists. I'm just refreshing my memory. So I won't spend any more time going over that in this video, except to say this second, what I'm calling a subtopic in this topic, this is actually topic 4 in my ordering scheme. So the first subtopic was the linked list. I took this organization scheme out of the textbook that I've mentioned previously by the author, whose name is Malik, last name Malik. So in that textbook, the author also he groups recursion together with linked lists, and this makes some sense to group these two topics together. And why does this make sense? Well, what is recursion? This is an opportunity for a cute joke to be made by a search engine, Google recursion. As you'll notice, usually this occurs in a search engine whenever you're in Google, the most well-known search engine, whenever you misspell a word. But as you can see, I've spelled it correctly. If I take the suggestion, it returns, did you mean recursion? Okay, recursion, recursion, recursion. So we're getting a sense of what recursion is just from looking it up on the internet, of course, and we could read some definitions here. It's often associated with computer science. There is a mathematical, there is in mathematics, the concept of recursion is used as well, which computer science was derived from in large part from mathematics. So it's not surprising that there's some overlap there. But usually when we talk about recursion in programming, we mean something like this, for instance. Now, this is an interesting example of recursion that is going to lead to Stack Overflow. So this is infinite recursion. So, but simply, main calls itself. And when a function calls itself, such as in this case, this is called recursion. The word recur is short for reoccur. So I think this just makes some sense. Recur, reoccur, reoccurring over and over and over again. And it's an interesting thing. Obviously, this is not a particularly useful example of recursion, but there are problems in computer science, classic problems like the N-Queens problem, the Knight's Tour, the Tower of Hanoi. All of these problems are very commonly solved with the use of a recursive function, solving the Tower of Hanoi, determining what makes a Knight's Tour, whether or not, yeah, a Knight's Tour. I'll talk about it in some more detail later, along with the N-Queens problem. We won't go into great detail on any of these algorithms, but all of them can be solved using recursion, and I'll talk about what it means to solve them later. All right, so this is infinite recursion because there is no main calls itself over and over and over again without any stop condition, without any base case, as it's usually called in programming. Okay. This is another cute joke. Recursion, if you look it up in the back of in an index, it often says C recursion. Yeah, I forgot that I forgot that I included this little bit of humor. Okay. Um, it is very typically the case that the first example of recursion is in writing a calculate factorial function, or maybe we just call it factorial. Factorial takes an integer n and it returns an integer. We know how to write this function using iteration. Let's see, we would say while we would say int result equal 1, and while n is greater than 1, we decrement it and we say result equal result times n, and we say n minus minus, something like this. It's either, I always get this backwards, or okay, so let's say cout iterative factorial, and 5. Are we going to see 120 here? I mean, let's comment out the recursive call. And we step to iterative factorial, n is equal to 5. We can see if we hover, result is initialized to 1, and n is greater than 1, 5 is greater than 1. We step into this, result is initially 1, so we take 1 times 5. Okay, so result gets updated to 5, and then we decrement n from 5 to 4, and then 4 is still greater than 1, so then we take 5 times n, which is now 4, so that's 20. We can see the values here in the locals window pane. Okay, so result is 4. We decrement n by 1 to 3, and now 3 is still greater than 1. And let's just cycle through this until n is not 1, not greater than 1, 1 is not greater than 1. So we terminate and we return the result, which is 120, which is n factorial. And it gets printed here. Okay, so that's an iterative version of a factorial function. What does it look like to write a recursive version of factorial? Int recursive. So one thing that we can be sure is going to happen here, because this is a recursive function, it's going to call itself. And it looks something like this. If n is equal to 0, then return, double equal to 0, return 1, else return, or we just call recursive factorial with n minus 1. And I think this is, it's in the slides, but okay, so this is the base. This is a bit of vocabulary. This is called the base case. This is called recursive case. So if you don't include a base case that does not include a recursive call in a recursive function, then you will have infinite recursion and Stack Overflow. So let's test this, and we'll set a breakpoint. So we'll say cout iterative factorial, recursive factorial. So once again, n is equal to 5. 5 is not equal to 0, so we're not going to return 1 yet. It's a very good idea in this case for me to open up the debug windows and show the function call stack. and have it over here. And this is nice. It's over in this alternative window pane, so we can still see the values of the local variables like yeah. Okay, so the main function called recursive factorial on line 25, excuse me, it called it on line 34 right here. And then we step to line 25, and this function is going to call itself. N is equal to 5 right now. It's going to get decremented. This function call stack is going to grow. I talked about this when we talked about the stack data structure. Pretty sure I have videos on the stack data structure. Yeah, 5 videos on stacks. Okay. So we will call recursive factorial with 5 minus 1 passed in as the argument. And notice that the function call stack grew. So we went from line 27 on line 27. We hit line 27, and then we went back up to recursive factorial call. N is now equal to 4. 4 is not equal to 0. We've not hit the base case yet. Okay. And we will call recursive factorial with the value 3, and the function call stack grew again. I'm sure there's some way in the debug windows to show we could keep track of the contents of memory. I've actually not poked into this. Keeping track of the return values. That's an interesting, certainly an interesting thing to think about. But for now, I guess let's continue what we're doing. N got decremented to 3, so 3 is not equal to 0. Okay, and we're going to step until n is equal to 0, of course, and n is equal to 2 now. And notice the function call stack just grows and grows. Okay, now n was previously equal to 1. It's going to get decremented to 0, so 0 is equal to 0, so we return 1. Nothing is printed yet. We haven't got the return value from recursive factorial. So we return 1. Okay, and let's see what happens. We return 1. The function call stack dropped. Everything got popped. Okay, and what are we printing here? We're printing 1. So, okay, not surprisingly, I made some mistake with the recursive factorial definition. Okay, yeah, it is a return. Excuse me. Let's step back through this. Return n times recursive factorial. Pardon my silly mistake. Yeah, there were a bunch of 1s over here that got returned, so obviously that doesn't make sense. Okay, let's redo this. Suppose it's good to make mistakes in a way. Okay, step, and nothing interesting is going to happen until we hit n equals 0. So let me just step through it. Okay, so now n is equal to 0. We return 1, but we're also returning the previous values of n, like 1, 2, 3, 4, and 5 times. So if n is equal to 1, we're returning 1. Okay, so let's look at it. So we return 1, and we come back here, and recursive factorial returned. So this is a way of keeping track of the return value. So n is equal to 1, it returned 1, so we got 1 times 1. and we hit the end of the block again, and we come back and it returned 1, but n is equal to 2. The function call stack is decreasing 1 by 1. Okay. And now recursive factorial returned 2 because we had 1 times 2, and n is equal to 3. So now recursive factorial, this call is going to return 6. So it returns 6, and n is 4 on this function call. And 6 times, you get the point. 6 times 4 is 24, returns 24, and finally n is equal to 5. And we return 120. And the function call stack, we're back in the main function. Okay, so that's the typical example of recursion that is in most every programming textbook. It would be good to be reminding ourselves of the definition of n factorial before trying to write code. Okay. Register stack pointer, it's worth being aware of. If you step into disassembly in Visual Studio, then it's nice to be aware that the function call stack, there's a pointer to the top of the word stack is used here. So it's nice to see the word pop is also used. So we pop the stack. Okay. There's the iterative approach, probably more familiar. There is a drawback to recursion, potentially. It's the necessity for keeping track of all those function calls. The performance may be slower than an iterative approach, but I can't recall if I've mentioned this yet, but when you're using data structures such as a node, which has some data of interest, and it is self-referential, so let's just call it link. So this data structure is defined in terms of itself. This recursive function calls itself. So if we highlight it here, you see there's a match in Visual Studio. So the linked list, the linked list data structure, certain algorithms, I didn't talk about any of them in previous videos, but certain algorithms such as stepping backward through a forward linked list, printing the list in reverse, certain algorithms are well suited to use recursive functions. I give a detail on that in these slides at some point. Okay. I give another example of Stack Overflow here, but this is related to the amount of memory taken up by a variable. It's not function calls, but it's kind of neat to be aware of. You can modify the size of the stack that's in Visual Studio if you like. That's what this slide is saying. Okay, we have seen big O notation. I believe I've posted videos on algorithm analysis. Yeah, searching, sorting, algorithm analysis. I'm lingering on this because I can't quite remember how much time I spent on this subject. Just refreshing my memory. Okay. In factorial, the bogus sort was what we saw. So it's not just a useful thing for the sake of demonstrating a relatively simple version of a recursive function. Factorial has other applications in computer programming. So I'm not going into a great amount of detail on recursion here, or I'm not writing a bunch of code, but Russian nesting dolls remind one of recursion. We get to a base case in which eventually there is no doll within another doll. These Russian nesting dolls. My grandmother had some of these and I used to play with them when I was a kid. I give a link to a couple of repositories in which I approximate a sphere using recursion and also generate the Shedepinski fractal using recursion. These are fairly well-known algorithms, definitely well-known to people who work in computer graphics a lot. And I guess I can find this fairly quickly, find the recursive call. It's in what I call 6.6. It's called 6.6 because I took it out of a particular textbook by an author, last name Angel, just in case anybody's interested. This seems like you might have the entire, I was about to say he has the entire textbook up here, but this this book right here, it was this version of it right there. So, chapter 6, section 6, he goes into detail on approximating a sphere with WebGL, which is the JavaScript equivalent of OpenGL. OpenGL is used for C++. So this is this function called divide triangle. It calls itself 4 times. In fact, I'm not going to get into details about what AB and AC and all these things are. They're, I think, line segments. But that's a recursive call. And the result of this is an approximation of a sphere. It this is a picture. I don't want to go through the process of getting remembering where I put my files on my computer so that it runs in this browser, the HTML code. But if you get a finer and finer approximation to a sphere, it kind of looks like this. This is a better example, except the starting point in that code right here is called a tetrahedron. It's not a cube. Okay, that's some extra detail for anybody who's interested. The Shedepinski fractal is it looks like a thing that many of us know as the Triforce. Shedepinski triangle, gasket, fractal. These are all different names for it. So you can use recursion to, recursion is typically used to draw this figure. Okay, just some nice applications of recursion. It is definitely not useful, it is definitely not useless. Okay, but reverse print. So we wrote a forward list that is, let's see. Let me pound included here. So linked list.h. And that error is saying that node is already defined. Or there's a conflict because there's a linked list and so there's a node in this linked list.h. So yeah, node of type T. So we wrote a constructor, a destroy list, not a destructor, and then a print. So I'm curious if we could write a reverse print. All right, and then we got length, insert first, insert get node, insert after a certain node, search for a particular value, delete node with a particular value, which was the most complicated algorithm. And then there's this reverse print. So reverse print, as you can see, calls itself. So let's create a linked list and step through, let's test the recursive functionality. The functionality of that recursive function. It's not intuitively obvious why I would use recursion to print this list in reverse, but I think if we step through it, it'll be helpful. So a linked list of type int and nums And with standard library data structures, we could use this convenient initializer list syntax, but with mine, we can't. So let's say nums dot insert insert first. We'll just call it a few times. We'll say 1, 2, 3. Very creative. And we'll say cout initial or printing list in forward direction. And we can say nums dot print. And notice the reverse print occurred there as an auto suggestion. Now, if we want to print the list in, of course, we want to print the list in the reverse direction and set a breakpoint so we can step through the reverse print function. Okay, so nums dot reverse print. And let's set a breakpoint right here. And let's see that an argument was required there. Okay, the current node. So current node, I forgot about that wrinkle. So let's see, how did I do this in the slides? Get the front node. Okay. Pointer to the front node. I may have written it a little differently in the, let's just see. What do I call it? Head node. Head. So node int star head equal get nums dot get node, and it takes node position, so it would be the 0th node, and we pass in head. And reverse print expects a pointer to the current node, not a node, but a pointer to it. Okay, so let's run and see what happens. So head is a node containing the info 3, because so in the forward direction we print 3, 2, 1. So we expect to see 1, 2, 3. So head contains a link to the info 2, and that contains a link to the node containing the info 1, and that contains a link to the null pointer, the end of the list. Okay, so we have to remember how the insert first function works, or the algorithm works. So let's step into that recursive function. Current is not equal to null because this is the it's the head node. So this is a pointer to the linked list, so it's not a node. Okay, so current is the pointer to the head node. So the info contained is 3, and the link points to the node containing 2, and that one contains a link to the node containing the value 1. So current is not equal to null, so we are going to execute the if statement. So if this if is not true, then what do we do? There is no, it's interesting to think about that. So we step in, we call recursive print with current arrow link. So current arrow link is this address right here, the address of the next node in the linked list. Not that there's a great deal of value in showing this. We can see the type, it's a pointer to a node of type int. We can see the function call stack is going to grow here. Okay, and we will see line by line the print in the reverse direction because we say cout current arrow info. But first we call this function. So let's pause for a minute and step. So we step back, and now current is the address of that second node in the linked list. it's not equal to null, so we call reverse print again. We haven't seen anything yet on the terminal. So we step to the last node in the linked list containing the value 1, and it's still not equal to null, but next we'll hit null. You can open up current, it contains the info 1. Okay. So we call reverse print with current arrow link. Current arrow link is equal to the null pointer, so let's see what happens. So current is equal to null here. So what do? We're going to pop the function call stack, and we step back to this instruction, cout current arrow info. So we pop the function call stack, got diminished by 1. We don't see anything on the terminal yet, but we're about to hit this cout statement. So we print current arrow info, and that is the value 1. So hopefully this makes some sense. Now we're going to print the value 2 and value 3. And then we go back to the main function and we return 0. So that's a fairly interesting example of a recursive function. Other examples are the in queens problem. I thought I had a nice picture of the in queens problem, but we'll write some recursive functions when we get to the tree data structure. I'm just giving a little bit of hoping to give a little bit of familiarity with recursive functions by spending a bit of time on it here. I don't have any assignments that I give on recursive functions at the moment, November 2023. But if you look up in queens, it's quite an interesting problem just to hopefully motivate people's curiosity. So this, how do we put 1, 2, 3, 4, 5, 6, 7, 8 queens on an 8x8, the typical standard size of a chessboard? How do we put them on a chessboard in such a way that none of them can attack any of the others? And that's a problem. First off, does a solution exist to this problem? And if so, how many? These are questions that a mathematician would likely pose. Does a solution exist? If so, how many solutions? And this is one solution, probably. It looks like a solution. Now, how long would a human take to determine one of these solutions? That's a good question. If we're on a 4x4 grid like this, it wouldn't be very hard to find at least one solution, and probably all of the solutions. But on an 8x8 grid, it becomes more challenging, and this is a problem that could be attacked using recursion and something called backtracking. And I've written some code that I could demo that shows how one recursive solution to the recursive approach to solving the in queens problem, but I'm not going to get into it in this video. So this can get extremely expensive very quickly. The 20 queens problem is computationally expensive, so we want to be careful with this. I haven't looked at the big O notation, the complexity of the n queens in the recursive case. That's not something is it big O n factorial where n is equal to the number of queens? That's a good thing to think about. But again, just as for people's interest, the Fibonacci sequence generation can be solved. You can generate a Fibonacci sequence using recursion. You can solve the Tower of Hanoi. This is a screenshot from the video game Mass Effect, where the programmers in that game decided to ask the players to solve the Tower of Hanoi, which is an interesting thing. It's only 4 discs, so it's not as complicated as 5 discs, but it was fun. And the Knight's Tour. So time 1, time 2, time 3. So you can see that this knight can move from here to here. The X's mark positions that the knight has already visited in previous time steps. So if the knight steps from here to here, and then from there to there, and then from there to there, and then from there to there, they've touched every position on the board without hitting any one position more than once. And that's related to something called an Euler circuit. Very fascinating stuff. It's related to graph theory. But we started out in this position at time one, excuse me, at time one, we are in this position, and maybe we came from the center of the chessboard. We moved it from here to here with the knight moves in L's, one up, two across, or let's not get into chess too much. We started at this position, moved from here to here, and then from here to here, and then from here to here. And I'm not showing every single time step here, but you could imagine how we got from here to here, possibly. Maybe we took here and went to here next, and then to here, and then to here, and then here. And then, okay, let's not get into that. But this is a neat problem. How do you do this? You could use recursion, right? This is this that I've shown is the step order here. It's one solution there on a 5x5 grid, and it's a really computationally demanding problem potentially. We step from position 1 at the top left to position 2, and then position 3, and then position 4, and so on, all the way until we get to step number 25. Okay, but yeah, I don't have any assignments on recursion. That's just my little short walkthrough on my short introduction to recursion. I think I might ask some quiz questions about it. Obviously, people on YouTube don't necessarily care about that detail. Depends on who watches this video.